The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Hello and welcome to Science for the People. I'm Rochelle Saunders. Today we're talking about the discovery, the search for, and the long history of some of the very smallest yet most abundant particles on our planet and in our universe. A little later on, I'll sit down with Donald Canfield to talk about his new book, Oxygen, a 4 billion year history. But first, Professor Ray Jayawardhana. Hello and welcome to Science for the People. I'm Rochelle Saunders. Here with me is Ray Jayawardhana. A renowned astrophysicist and an award-winning science writer, Ray is a professor and Canada Research Chair in Observational Astrophysics at the University of Toronto. A graduate of Yale and Harvard, he uses many of the world's largest telescopes to explore planetary origins and diversity. He is the co-author of over 100 papers in scientific journals, and his research findings have made headlines worldwide, leading to numerous accolades and awards. He's here today to talk about his new book, Neutrino Hunters, the thrilling chase for a ghostly particle to unlock the secrets of the universe. Welcome to the show, Ray.
Happy to be here.
So we should probably start with a gentle introduction. What are neutrinos for the uninitiated?
Neutrinos are a type of elementary particles. They're all around us. In fact, they're the most abundant type of matter particle in the universe. They have rather quirky characteristics, which is what makes them fascinating, puzzling, and interesting.
So why are they so exciting to physicists, and why did you decide to write a book about them?
Well, because, as I said, neutrinos, we're basically being bombarded by neutrinos in all directions. They come from the nuclear furnace at the heart of the sun. They're neutrinos produced in the upper atmosphere of the Earth when cosmic rays interact with atoms up there. And there are even neutrinos produced right beneath our feet from the radioactive elements decaying in the Earth's interior. So they really are incredibly ubiquitous, but that also means they are connected to a wide range of phenomena, both on the cosmic scale, but also in the subatomic realm. So we could learn about an incredible diversity of natural phenomena from the study of neutrinos.
So I follow physics news pretty closely. I mean, I'm a layperson. I don't have any kind of advanced knowledge of this stuff, but I find it really interesting. And one of the things I've noticed is I don't hear a lot about neutrinos, even though I sort of know in the background there's a lot being done with them and searching for them. But I don't hear a lot about them in the media. Do you think they're getting a short shrift in the media, or why do you think we don't hear about them as much?
Well, partly because I guess particles in general are not the easiest kinds of things to visualize, in our everyday experience. But neutrinos did make front-page headlines a few years ago when there were reports of them possibly traveling faster than the speed of light.
I remember that.
That led to a huge brouhaha in the media, and lots and lots of bad neutrino jokes. Unfortunately, or fortunately, depending on your point of view, it turned out to be much ado about a faulty cable. So neutrinos, while they travel very, very close to the speed of light, do not exceed the so-called cosmic speed limit that Einstein proposed.
So, since the book is called Neutrino Hunters, we should probably talk about some of the people who've headed up the search over the years. Who first theorized the existence of neutrinos?
It's indeed the book is both the science about both the science and the people interested and pursuing the study of neutrinos. These were particles that were hypothesized, or in some sense invented, long before they were confirmed experimentally. Back in 1930, Wolfgang Pauli, a brash young physicist, who was struggling with, along with a number of his colleagues, struggling with a puzzle that had to do with the appearance of, or the disappearance of energy during the so-called beta decay type of radioactive decay. So scientists, when they first discovered the phenomenon of radioactivity, fairly soon they realized that it comes in three different forms, which they creatively dubbed alpha, beta, and gamma. For two of the three types of decay, they had no trouble balancing the books. But for beta decay, it appeared that when an atomic nucleus underwent this transformation, it emitted an electron, but some other energy seemed to go missing. And this remained a puzzle and seemed contrary to a sacrosanct law of physics, the law of energy conservation. So it is to find a solution for this mystery that Pauli proposed a whole new yet unknown particle, which later came to be known as the neutrino. This was a rather radical step at the time because physicists knew of only two matter particles back then. So to propose a third matter particle seemed like a big step, and Pauli himself in some ways wondered whether he was barking up the wrong tree. He came to even supposedly bet a case of champagne against the experimental discovery of the particle he himself proposed. And it took some 25 years before physicists had experimental confirmation of Pauli's proposed particle.
So 25 years is a long time between theory and direct experimental evidence. Why did it take so long?
For multiple reasons. Well, one of which was that through most of the 1940s, a lot of physicists on both sides of the Atlantic focused their efforts toward the Second World War. So that, you might argue, distracted them perhaps.
That is quite a distraction.
Indeed. Though, as many people realized, atomic bombs themselves are copious sources of neutrinos. So in the end, when in the early 1950s, physicists started to think about how you might go about detecting neutrinos, they thought of using the neutrino bursts coming out of a bomb explosion as a good source. And in fact, the two physicists who first ended up detecting the neutrino experimentally, their first thought was to set up a bomb explosion and deploy a detector nearby to detect the neutrinos outburst. Thankfully, they didn't end up doing that. Instead, they set up their detector next to a nuclear reactor, and that's how they confirmed the existence of this ghostly particle.
So who were the scientists that had the luck, or I suppose, or the ability to find the first neutrinos experimentally?
There were two scientists associated with Clyde Cowan and Fred Rines were the two scientists who made the experimental discovery of neutrinos in the early to mid-1950s through a series of experiments.
And neutrino experimentation kept going after this. It wasn't like we found the evidence and sort of the case closed. There were continuing experiments all throughout the Cold War.
Indeed. One of the other physicists that got on the trail of neutrinos rather early in the 1950s was an American physicist by the name of Ray Davis. He ended up chasing neutrinos coming from the sun because if we understand how the sun is powered through nuclear reactions, then we would expect a continuing flux of neutrinos arriving here on Earth from the sun's nuclear furnace. So Ray Davis, along with a colleague who was a theorist, John Bacall, decided that they could try to trap neutrinos coming from the sun and therefore confirm independently the powering mechanism of the sun. When they first set up the experiment in a mine in South Dakota, the early results came up short. They found many fewer neutrinos than were expected to arrive on Earth if we understood the nuclear furnace inside the sun. And it took some 30 years and a lot of work, and eventually the independent evidence from two other experiments before scientists were able to understand the reason for the solar neutrino deficit. it turned out that we did understand how the sun works, but we didn't understand fully the chameleon-like nature of neutrinos. In other words, it turned out that neutrinos come in 3 different flavors and morph among them. And at first, scientists were only registering one type of neutrino. That's the reason that it appeared that there was a deficit of neutrinos coming from the sun. And this discovery of so-called neutrino oscillations, the morphing of neutrinos among 3 flavors, has opened up a lot of new avenues for exploration. For one thing, it confirmed that neutrinos are not massless particles, as initially thought, that they do indeed have a tiny, minuscule amount of mass associated with them. Otherwise, they couldn't go through this kind of transformation. Second, the details of this behavior, the oscillations, could lead us to new physics beyond the standard model of particle physics. So there are a number of experiments happening around the world today trying to characterize neutrino oscillations precisely in order to not only understand that phenomenon, but what the implications might be for particle physics in general.
You're listening to Science for the People. We're talking with Professor Ray Jayawardhana, astrophysicist and author of the new book, Neutrino Hunters, The Thrilling Chase for a Ghostly Particle to Unlock the Secrets of the Universe. There's a couple of quite interesting characters who have been involved in hunting neutrinos throughout the years. One of them that I found really quite interesting was Paul Dirac.
Indeed. Well, Dirac was a theorist. There's a whole, I should mention that there's a wonderful biography of him out there. He was a rather, perhaps a shy or somewhat reclusive kind of personality, and someone who tended to think very literally. And he was a theorist who was involved in the development of quantum mechanics, and had something to say about neutrinos as well. There are a number of other characters that I describe in the book whose lives were intimately connected to the story of the neutrino. One of them is, two of them were Italians, it turned out. Ettore Majorana, who was a reclusive genius who disappeared without a trace at age 32, presumably while on a boat from Sicily back to Naples, where he had a teaching position. And to this day, no trace of him has ever been found. And it is said that for years in Italy there were stories of Majorana sightings, just like we talk about Elvis sightings in America. The other Italian that had a lot to do with neutrinos was came by the name of Bruno Pontecorvo. He was a protege of Enrico Fermi in Rome when Fermi was a young professor there. Later on, actually lived in Ontario for a while, worked at the Chalk River Laboratory, and ended up going with his family moving to England, where he worked at an atomic research facility. And the whole family defected one fine day after a summer vacation on the European continent to the Soviet Union at the peak of the Cold War tensions. So that created an international manhunt, so to speak, certainly generated headlines across the globe about this physicist who either some speculated might have been a Soviet spy all along, or at least had taken valuable nuclear secrets with him behind the Iron Curtain. You can imagine the kind of news that generated and the speculation that followed. And in fact, a few years later, he did appear at a press conference in Moscow and explained his own reasons for defection. So there are a number of these kinds of colorful and perhaps unusual characters associated with the neutrino hunt over the years.
It's really interesting to hear about sort of the personalities of these people, because we quite often, we read books and we hear about the work and we talk about the experiments and the things that have come from the experiments. But some of the most interesting stuff is these people's lives and kind of how science either affected their life or what the world they grew up in. It was really interesting to read about that.
Indeed, and some of the insights that these people had, it took decades for us to get to a point of being able to understand the full implications and to experimentally try to verify their proposed ideas. Another person that I briefly sketch is a German mathematician by the name of Emmy Noether, who at the time had a lot of trouble, despite coming from a rather mathematical family, in pursuing a higher education in mathematics. She wasn't allowed to enroll at the local university simply because she was of the wrong gender. And she basically audited the classes and still aced the course, and was later able to pursue a PhD. When she applied for a teaching position at the university, there was a lot of disagreement about whether a woman could be offered a professorship. One faculty member, they protested, what will our soldiers think when they return to the university and find that they're expected to learn at the feet of a woman? Others came to her defense. David Hilbert, most famously a famous mathematician, a prominent mathematician, he was infuriated by this discrimination, and he argued, we are a university, not a bathhouse, so why should the gender of the applicant matter? Still, he was unsuccessful, and she wasn't offered a permanent position, only a guest lecturer position. Later, she came to the United States to be a professor at Bryn Mawr College in Pennsylvania. So we learned not only about the science these people did and the insights that they had, but also about the environment in which they were working and the social and political forces at work. So it's conveys the sense that science is very much a human quest done by individuals and groups of people that often get caught up in what's happening around them beyond the science itself.
This is Science for the People, and we'll be right back with more from Professor Ray Jayawardhana on his book Neutrino Hunters, The Thrilling Chase for a Ghostly Particle to Unlock the Secrets of the Universe.
Science for the People is a weekly radio show exploring everyday life from a scientific perspective. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to connect with us on Facebook, Twitter, and Google+, or to subscribe to the podcast in iTunes. And now, back to the show.
Welcome back to Science for the People. I'm Rochelle Saunders. I'm here with Professor Ray Jayawardhana, astrophysicist, Canada Research Chair in Observational Astrophysics, and award-winning science writer. He's also the author of the new book, Neutrino Hunters, The Thrilling Chase for a Ghostly Particle to Unlock the Secrets of the Universe, which is what we're talking about today. You mentioned Majorana a little bit back, and I want to get back to him because he had some interesting ideas about neutrinos, and some of them I think are still open today.
Indeed, scientists are still one of the topics that he wrote about in a research paper is the question of whether neutrinos and their antimatter twins, the antineutrinos, whether they behave in identical ways. And it's only now, many decades later, that we have the experimental capabilities to try to address that big question. And that question has broad-ranging implications. It could lead us to an answer to a profound and difficult puzzle, which is how come the universe has come to be dominated by matter? Because we expect that there should have been equal amounts of matter and antimatter right after the Big Bang, and yet we are here and we are living in a universe dominated by matter. How did that asymmetry come about? That's been troubling physicists for decades, and the nature of neutrinos and antineutrinos could give us important clues to try to understand the reason. It's not a simple problem. It's because the kind of asymmetry that we would be looking for is very, very small, but still sufficient to account for the universe coming to be dominated by matter. So there are a number of experiments underway now trying to test whether Majorana was right or not about the asymmetry or symmetry between neutrinos and their antimatter twins.
One of the fascinating things that I'm constantly reminded of while I was reading your book was how long the timescales are for some of this stuff. We have these ideas, we find these problems, we have these ideas and these theories, and then it's decades, 30, 40 years before we can actually test this stuff and try and confirm it, which is a really long time. Science is slow.
Yeah, for the most part, you've got to be rather patient in the neutrino business. One reason is, you need the technology, the detectors, to be able to do this kind of work experimentally. But the other is simply the nature of neutrinos themselves. I mean, the fact is that they hardly ever interact with the environment. They zip right through, our bodies and the walls of your room and through the Earth itself, which means it takes a lot to try to trap just a handful of the millions and millions and millions of neutrinos that would pass through a cubic square. Pass through a square centimeter of a detector. So that is indeed an incredible challenge. I mean, it's also one of the reasons that makes neutrinos so interesting, because you could detect neutrinos coming from very distant astronomical sources like a supernova explosion, because they do pass through anything and everything pretty much. But that also means when you try to detect them here on Earth with a neutrino detector, you're only capturing a few of the many that pass by. Makes it rather challenging experimentally.
You mentioned supernovas, and I know there was a lot of excitement about a particular supernova that happened a number of years back. I can't remember.
In 1987,
yeah.
So that was the nearest supernova explosion that we've seen in some 4 centuries. This was a supernova that exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, and some 24 neutrinos, almost certainly originating from that supernova, were registered by 3 different neutrino detectors around the globe. This was a monumental finding. Even though just a handful of neutrinos were detected, they provided independent confirmation that we have a pretty good idea as to what happens during a supernova explosion. In other words, these neutrino detections confirmed the broad outlines of our theories for how and why supernovae explode. But back then, we had only a few relatively primitive neutrino detectors deployed. If a supernova were to explode today, anywhere in the Milky Way galaxy, scientists expect to record up to hundreds of thousands of neutrinos. Imagine how much more one could learn from such a vast number of detections. For one thing, you could almost follow the unfolding of this explosion over up to maybe 10 seconds by monitoring the neutrino flux coming from it. And you could, in principle, use the neutrinos to determine whether that explosion resulted in a black hole or a neutron star, because depending on the outcome, the neutrino flux would either come to an abrupt halt or would decay a bit more gradually. And you might also learn something about neutrinos themselves, because they have to pass through incredibly dense outer layers of a collapsing star on their way out, and that would affect the oscillations of neutrinos. So we might learn something about the behavior of neutrinos themselves in extreme conditions by observing neutrinos from a galactic supernova that we could record with these detectors. I should mention that the largest of the neutrino detectors today is called IceCube. It's quite a fascinating new type of observatory that uses a cubic kilometer of ice deep under the South Pole as the detector. So it's kind of an extreme. It's a kind of a marvel of extreme engineering, where scientists have buried some 5,000 sensors into the ice by drilling deep holes within it, and turned this large chunk of ice into a neutrino detector that's very, very sensitive and is already making some interesting discoveries.
I'm glad you mentioned IceCube in Antarctica, because it was one of the ones I wanted to talk about. It's fascinating, and you provided an interesting diagram in the book that shows just how big this thing is. You sort of have the experiment pictured, and then you have a tiny little Eiffel Tower next to it. And just the size of these experiments they're immense.
Yeah, and they have to be because of the reluctance of neutrinos to interact with the environment. The interactions are rare, and that's why scientists have to build very large volume detectors to increase the odds of detecting even a few neutrinos. Basically, increase the odds of chance encounters that lead to the detection of neutrinos. The other thing is they often build neutrino detectors, I should say almost always build neutrino detectors deep underground or deep under the ice. The reason for that is to basically filter out the noise from other particles in the environment, like cosmic rays, because most of those other particles don't penetrate through kilometers of ice or ground, but neutrinos have no trouble at all zipping right through. So by burying these neutrino detectors deep underground or deep under the ice, you can filter out the noise and focus on the neutrinos alone.
Some of these things... sorry, go ahead.
No, I was going to say that I had the opportunity to visit one of these underground laboratories where there's a neutrino experiment happening, namely the Sudbury Neutrino Observatory in northern Ontario. It's located in a working nickel mine, and I, along with the director, we took the elevator down at 7 o'clock in the morning with a couple of dozen miners, an elevator cage that descends into the bowels of the earth some 2.5 kilometers below the surface. And then you trek through a couple of kilometers along a muddy, dusty tunnel, and then you come to the entrance to this laboratory, and you have to go through an elaborate cleaning ritual, taking a shower and changing your overalls and walking through an air shower before you're allowed to enter the inner sanctum, because the inside of Snow Lab is incredibly clean, and with shiny walls and dust-free air, whereas the mine outside is quite grimy and dusty. In order to safeguard the integrity of the experiments, they have to clean the inside. They have to keep the inside of the lab incredibly clean. And it's also kind of ironic to think that you've descended a couple of meters underground where the sun never shines to deploy a detector that was originally meant to study neutrinos coming from the sun. So you're basically going deep underground to look at the inner workings of the sun that you can't see from down there.
I love the juxtaposition of some of the stuff with neutrino experiments. You build something really big to find something really small. You bury something under the ground to find something out about the sun. It's really interesting. Indeed.
It's quite a fascinating story, both the science and the people, and in fact, even the engineering to do with the experiments.
There was one example, and I don't have the name of it, where they had to move something through a village.
Yeah, you're probably referring to the Katrine experiment in Germany, where they built a gigantic spectrometer for a neutrino experiment, and realized that they couldn't take it to where it needed to be deployed because the roads in the region were too narrow. So they had to take the long way around and first put it on a barge and a number of different vessels, take it all the way around the Mediterranean and around England and re-enter Germany in the north to get it to where it needed to go. So indeed, there are some humorous anecdotes to do with some of these experiments. Another one that I relate in the book has to do with the preparations for deploying a neutrino detector in the ocean ended up registering acoustic sounds made by whales in the deep ocean. So there are all these lovely connections, and there's a third experiment where they're using lead recovered from an ancient shipwreck for the experiment, because that lead has by now lost most of its natural radioactivity. So there are lots of lovely anecdotes that feed into the overall narrative of Neutrino Hunters.
So how many of these experiments are actually running right now?
I couldn't give you an exact number, but I would say dozens of neutrino experiments are underway around the globe. They basically come in three different types. There are neutrino experiments like IceCube or SNOLAB, where they are built to register neutrinos coming from natural sources, either astronomical sources or sources high in the atmosphere of the Earth or deep underground. And then there are neutrino experiments where scientists intentionally produce beams of neutrinos, for example, at Fermilab near Chicago, and shoot them through the Earth and detect them some distance away. For example, in the case of Fermilab, the detector is in a mine in Minnesota. The idea there is that you could produce a particular type of neutrino beam, say a beam of electron neutrinos, shoot it through the Earth some tens or hundreds of kilometers, and make the detections at the far end and test how those neutrinos have morphed into other types. And then there's a third type of neutrino detector where scientists deploy their experiments next to or near working nuclear reactors. They're basically using neutrinos which are byproduct of nuclear reactors to feed their experiments.
You're tuned in to Science for the People. Today we're talking about the history of the discovery of those most elusive of particles, the neutrino, with astrophysicist and author Jayawardhana. I want to talk a little bit, and we're probably going to enter the realm of speculation here, but what some of the potential practical uses of neutrinos might be, because obviously we've learned a lot about them. We've learned a lot about cosmology and the way the world works. But do you think we'll ever actually be able to put neutrinos to use?
Well, there's certainly proposals for how you might put neutrinos to work. One of the most serious avenues that's being pursued is the idea that neutrino detectors might come in handy for keeping tabs on nuclear reactors. Because anytime you run the nuclear reactor, you're producing also as a byproduct a gigantic flux of neutrinos. So if only you could deploy neutrino detectors next to nuclear power plants or nuclear reactors, then you could really continuously keep tabs on their operation. Right now, international nuclear monitors do periodic inspections to make sure nothing untoward is happening at many of these reactors. But that's not necessarily the most precise or comprehensive way to do that. So you could imagine someday neutrino detectors could come in handy for monitoring nuclear reactors and therefore in some way contribute to peace and stability of the world. There are other perhaps more far-fetched proposals, such as using neutrinos for communication. Because they can travel right through the Earth, you might imagine producing and shooting a beam of neutrinos right through the Earth and communicating that way instead of having to bounce a signal of satellites or send it along fiber optic cables around the Earth. You might save a few milliseconds that way. And people have even talked about advanced civilizations using intense neutrino beams to communicate across the vast distances of the galaxy. And there are many, many other ideas about how neutrinos might be put to use, even for more economic activities such as oil prospecting, because neutrino beams, if you could produce them with sufficient intensity, could be used sort of like the way you might use X-rays to look for cavities in your teeth, to look for formations in the ground that might be associated with either mineral deposits or oil. So you might end up. You might think of using neutrinos for geological exploration as well.
So I'm assuming before we can do kind of anything really practical with neutrinos, we might have to shrink down the size of the detectors a little bit.
Well, that isn't always, that isn't the easiest thing to do. As I said, neutrinos hardly ever interact with anything, which means to increase the chance of an interaction, you do need to have a fairly large volume detector. Now, the more intense, for example, in terms of neutrino detectors that are deployed near a nuclear reactor, for example, they don't have to be incredibly big, depending on how close you are to the neutrino source. They could be relatively small and manageable, but still, don't hold your breath for a mobile phone using neutrinos, for example. That's not going to happen.
Oh, that sounds like space. I love that. Space age. I'm going to use my neutrino phone.
Yeah.
Ray, it was great to have you here. Thanks for joining me.
Pleasure.
If you want to learn more about Ray Jayawardhana, his work, or his book Neutrino Hunters, The Thrilling Chase for a Ghostly Particle to Unlock the Secrets of the Universe, you should check out his website at www.rayj.net, and we'll be sure to put that link in our show notes at our website, scienceforthepeople.ca. Stay tuned. After the break, I'll be back with Donald Canfield to talk about the story of oxygen on our planet and his new book, Oxygen, A 4 Billion Year History.
On the next episode of Science for the People, we're on the frontiers of medicine, from the fabulous to the foolhardy. We'll talk to Dr. Kevin Fong, co-director of the Center for Aviation, Space, and Extreme Environment Medicine at University College London, about his book, Extreme Medicine, How Exploration Transformed Medicine in the 20th Century. And we're joined by Dr. Sidney and Justin McElroy, hosts of the podcast Sawbones, a marital tour of misguided medicine. That's next week on Science for the People, on your local radio station, or online at scienceforthepeople.ca.
Welcome back to Science for the People. With me is Donald Canfield, professor of ecology at the University of Southern Denmark and director of the Nordic Center for Earth Evolution. He uses the study of modern microbes and microbial ecosystems to understand the evolution of Earth's surface chemistry. He uses the study of modern microbes and microbial ecosystems to understand the evolution of Earth's surface chemistry and biology through time. He received his PhD at Yale University and is a member of the National Academy of Sciences. He's here today to discuss his new book, Oxygen, A 4 Billion Year History. Welcome to the show, Don.
Well, thanks a lot. Thanks for having me.
So what inspired you to write a book about oxygen?
Well, I guess I've been working with it for most of my academic career, so I thought it might be fun to try to sit down now and finally put some structure to a lot of the ideas that have been developing over the last years.
So where does oxygen come from?
Well, the easy answer is that oxygen comes from plants and a certain kind of bacteria called cyanobacteria. I mean, those are the ultimate producers of oxygen. If you want to understand, though, why there's oxygen in the atmosphere, that's a much more difficult question to answer.
So how did oxygen get to Earth?
Well, oxygen, there was no oxygen in the Earth's atmosphere before there was the evolution of the organisms to produce it. So the Earth began as a planet without any oxygen whatsoever. So at some time in Earth history, and that's one of those things which we like to discuss a lot in our community, a certain type of bacteria called cyanobacteria evolved, and they started to produce oxygen. Now, the interesting thing about that is that it's likely, though, that oxygen didn't begin to accumulate in the atmosphere right away. And that's because you could sort of imagine it like this, that on the one hand you have organisms that are able to produce oxygen, but you also have an Earth environment which is influenced by things that are happening within the Earth. So, for example, volcanoes spew out hydrogen gas, for example, and hydrogen gas just loves to react with oxygen. So that even though cyanobacteria first started to produce oxygen sometime long ago in Earth history, it probably didn't accumulate just then into the atmosphere.
So how do we know that cyanobacteria helped kickstart the oxygen levels in Earth?
Well, they had to, because they're really the only process that we're aware of that can produce significant amounts of oxygen. There are some chemical processes which can produce a little bit, and there's even a very interesting other biological process that can produce just tiny, tiny amounts. But the only organism that we're aware of, and the only pathway we're aware of that can produce lots of oxygen is biology, and cyanobacteria were the first.
So cyanobacteria produces a lot of oxygen, but most life on Earth needs oxygen to even survive. Does cyanobacteria not require oxygen to get started?
No. It's a very interesting idea that is used to explain the evolution of cyanobacteria. Probably your audience will be aware that cyanobacteria are photosynthetic, so they use the light of the sun in order to provide the energy for their metabolism. But there were a whole bunch of types of different photosynthetic organisms before cyanobacteria that didn't produce oxygen. They're called anoxygenic photosynthetic bacteria. And our best understanding is that two types of these fused together into a single type of organism, and it was that organism that started to produce oxygen.
So how far back are we talking here? At what point did Earth's atmosphere go from, approximate point, did Earth's atmosphere go from not a whole lot of oxygen to enough oxygen to support the kind of life we see today?
Okay. Oh, well, okay. There are several ways of approaching this. The easy answer is that about 2.3 billion years ago, there was the first large-scale accumulation of oxygen in the atmosphere. It's something called the Great Oxidation Event, and that's pretty obvious in the geologic record. Now, cyanobacteria probably evolved long before that, and we have some evidence that it was at least 700 million years before that the first cyanobacteria evolved. So as I said before, even though cyanobacteria evolved and were able to produce oxygen, it probably didn't accumulate into the atmosphere until sometime after. And another point that I'd like to make, which I think is kind of interesting, we actually are used to thinking about oxygen being critical for life on Earth, and it absolutely is for much of the life that we're aware of. But there's a whole bunch of life on the Earth that doesn't give a hoot about oxygen. In fact, they're much happier not to have it at all. And these are the so-called anaerobic organisms, and those were the organisms that would have populated the Earth before oxygen began to accumulate.
So you mentioned the Great Oxygenation Event. Did I pronounce that correctly?
Yeah, pretty close.
The Great Oxygenation Event. Now, you said that this is visible actually in the geological record. How fast did this happen? Was it something that happened quite quickly on a geological timescale, or did it take a really long time?
Boy, that's something that we're really working on. Quickly. Let's in stages. It probably played out over about 300 or 400 million years, but the actual progression from what the geochemical record would say is very little oxygen to what became actually rather detectable oxygen probably played out over tens of millions of years or something like that. Sounds like a long time, but on geological timescales, it's actually not so much.
Do we have any idea what caused it?
Well, in broad terms, I think we do. One line of thinking, if you recall, I mentioned that cyanobacteria probably evolved long before oxygen accumulated, and one of the reasons oxygen didn't accumulate is because of hydrogen coming out of volcanoes. Well, the rate with which hydrogen comes out of volcanoes is probably coupled to how fast the Earth's mantle cycles and turns over, and that depends on how hot the mantle is. And the fact is that the mantle has been cooling down through time, so the whole rate with hydrogen has been pumping into the atmosphere has actually slowed down. So you can kind of imagine a titration point where the hydrogen production rate dropped to the point where oxygen could actually first start to accumulate, and that is what many of us think actually signaled the Great Oxidation Event. Does that make sense?
Yeah, it does. So. Sorry, I got lost in my own questions.
Yeah.
So we really think of oxygen as being tied to the beginning of life on Earth. What makes oxygen such a great chemical or element for the use of life?
Actually, oxygen isn't really coupled to at least the origin of life on Earth. That happened long before there was any oxygen around. So I think that's a really important point to make. But what makes oxygen so great? Well, it's a really high energy compound. You know, we're heterotrophic organisms, which means that we take oxygen in our case and we burn French fries or yogurt or whatever we had for breakfast and make energy that way. And you can get a whole lot of energy out of it if you use oxygen compared to other possibilities. And what are other possibilities? Well, sulfate is a possibility. There's lots of organisms that can take French fries and yogurt, let's say, and they can react it with sulfate and live that way. But the amount of energy you get out of it is much, much, much lower. So oxygen is just a really great high energy compound to burn with organic matter.
You're listening to Science for the People. I'm on with Donald Canfield, professor of ecology at the University of Southern Denmark and author of the book Oxygen, A 4 Billion Year History. You mentioned that there is evidence for the oxygenation of the planet Earth in geological record. How do we know as much as we do about the kind of history of oxygen on the planet? I'm assuming there's not a lot of really hard evidence insofar as animal records or fossil records from, 4 billion years ago. How is some of this work being done to determine how the planet was oxygenated?
It's actually, there are a lot of different avenues people are taking to try to understand this story. And let me try to explain two. One is that oxygen is reactive with lots and lots of different types of compounds or minerals that you can find in rocks. So if you're familiar with a mineral called pyrite, maybe you are. It's fool's gold.
Yep.
Well, pyrite really reacts pretty fast with oxygen. So I explain this in the book. If you try this experiment, you just buy a piece of pyrite and you go put it out in your backyard and you come back maybe in half a year or so and see what happened to it. Well, hopefully you'll see that it's reacted with oxygen and it's turning into rust. Well, if you go way back in Earth history and you start looking at sediments which were ancient river beds, you can find that you see pyrite in these riverbeds, and that's really weird because normally you don't find pyrite in modern riverbeds because it oxidizes away into rust. So the fact that you can see pyrite in these ancient riverbeds is telling you that oxygen was very, very low in concentration. And I think that's a good illustrative example. There's lots of other examples I can get into which would actually yield more or less the same result. And now there's another thing. You mentioned fossils. There actually are some kinds of fossils that we might be able to look at, and some of them are called biomarkers. And biomarkers are organic compounds which are part of our cellular material. And one type of biomarker which people are really pretty interested in is a type called sterols. Cholesterol is an example of a sterol. And if you go back in the geologic record, you can find sterols in rocks that are as old as about 2.7 billion years ago. And the interesting thing about sterols is, as far as we know, they have an absolute requirement for oxygen to be made. So that means that way back in that time, 2.7 billion years ago, even though we think oxygen levels were really low, there might have been just a little tiny bit of oxygen around that organisms could use to synthesize sterols with. So it's putting these kinds of different types of information together, which helps us to try to calibrate oxygen levels and try to understand the history of when oxygen first started to appear and then first started to accumulate in the atmosphere.
It was really interesting because I had never thought before reading your book of things like the history of certain elements on our planet. You just think they're here, they've always been here, that's the way our planet is. So it was really interesting to think of it as more something that not really evolved, but kind of its circumstances evolved.
Yeah, that's right. I mean, the Earth is just such a fascinating planet because it has evolved dramatically through its history. There's no question about that. But it's at the same time, it's also been a planet which has been so amazingly conducive for life. So it's just a beautiful place to be.
So why did scientists like yourself start exploring where the oxygenation came from or when it happened? I guess I'm asking to some extent, why do we care about the history of oxygen?
Well, I think that from my perspective, and probably from lots of people's perspective, if we want to understand why we're here on this planet, we need to know why there's oxygen. And in order to understand why there's oxygen, we immediately start to think about what its history is. And that's sort of the entrance point, maybe, that I and many people have taken into trying to understand this problem. It's intrinsically a fascinating scientific puzzle, which is also another reason. But as far as we know, advanced life, like human life, is unique on the Earth. The Earth is a unique planet as far as we know. And to understand our place in this planet, we really do need to understand something about oxygen.
So what are some of the, or maybe some of the major unanswered questions about the history of oxygen?
Oh, there are so many things that are unanswered. If I were to sort of summarize, I think some of the real critical ones, they would be, when actually did cyanobacteria first evolve? We really don't know that very well. During this great oxidation event that I talked about, how high did oxygen levels actually become? Then after that, what has been the history of oxygen up until the present time? I go through the book and I try to outline our best understanding of that history, but I would say that much of it is still very poorly known. So our understanding of that history needs lots and lots of detail. And one of the things that I think is really interesting is there any relationship between the evolution of animal life and increases in atmospheric oxygen? There seems to be some geochemical evidence that around the time animals first started to evolve, there was an increase of oxygen in the atmosphere, and it's a very interesting issue as to whether or not there could have been a relationship there. And if there is a relationship there, it would be because animals actually have a reasonable requirement for oxygen. So it could be there's some kind of a relationship between biological evolution and the evolution of the chemistry of the planet. Those, I think, are some of the real sort of still fundamental, deep, and fascinating questions with respect to oxygen. I'm sure there are lots more, but those are the ones that I hope to invest some time and energy into in the next years to try to understand.
You mentioned the connection between oxygen levels and sort of larger animals evolving. I've heard, and I don't remember where, and I have no idea if this is true or not, that possibly the evolution of like the really large life we've seen on the planet in the past, things like the dinosaurs, was potentially tied to a higher level of oxygen in the atmosphere. Is there any truth to that?
Perhaps. I don't know if you've heard about these gigantic dragonflies and stuff that occurred around 300 million years ago. Well, this was a pretty interesting period in Earth's history. This was a time when there were lots and lots of coal swamps that were forming around low-lying areas on the Earth, and this is a detail which isn't really a detail. It's actually kind of important. Cyanobacteria produce, and algae, of course, now, and trees produce oxygen. But the way you get it to stay in the atmosphere is to have the organic body mass produced by algae and cyanobacteria and trees get buried in sediments as either coal or organic matter or stuff like that. So there was a lot of coal being deposited, which meant that there was a lot of oxygen that was produced into the atmosphere. And my thesis advisor and myself many years ago constructed some models to try to understand how high oxygen might have gotten. We thought that it might have actually increased by 50% or more over what we have today. And it correlates really nicely with a time when there was giganticism among flying insects and other insects on the Earth's surface. So it could be there was a relationship between biology and oxygen at that point in Earth history as well.
So we know that oxygen levels have changed in the past, but are they changing still today?
Yeah, I actually get asked that question a lot, and not in a perceptible way. And let me backtrack a little bit. Techniques are sensitive now that you can measure a decrease in oxygen in the atmosphere, which is related to the combustion of fossil fuels. So that's actually pretty neat. You can see CO2 going up, and you can see oxygen coming down. But the amount that oxygen is coming down is very small and very, very difficult to measure. So in fact, even though fossil fuel burning might be worried about it for other reasons, we don't have to worry about it really with respect to oxygen. We don't have it would just be impossible to remove oxygen to any significant amount through the burning of fossil fuels. So it's pretty stable in the foreseeable future.
Don, thanks so much for being here.
My pleasure.
If you're interested in learning more about Don Canfield and his book Oxygen, A 4 Billion Year History, you can find links to help you get started on our website at scienceforthepeople.ca. While you're visiting, do also click over and find us on your favorite social media network, where you can get the latest news from the Science for the People team. You can find us on Twitter, Facebook, and Google+. Speaking of our website, if you haven't stopped by in a little while, you may have missed our new store, where those of you wanting to show your enthusiasm for Science for the People can find a few select items we hope you'll enjoy. Those of you we've met will know that our team takes coffee intake very seriously. So we've created an official Science for the People coffee mug, available in both an 11-ounce size for modest caffeine drinkers and a 15-ounce size for those who need a little more to get you going in the morning. We've also added a range of shirts and hoodies in men's and women's styles for those who'd like to wear the Science for the People colors and spread the word. To check out the official Science for the People branded store, visit our store website at scienceforthepeople.ca/store. And if you do, we'd love to hear your feedback. What official Science for the People items do you love? What other items would you like to see made available? And speaking of feedback, we love to hear from you. You can email us anytime at feedback@scienceforthepeople.ca. Send us your thoughts on the most recent show, or pass along your ideas for new shows. You can also leave your thoughts in the comments on individual episodes on our website, send us a message, or comment on our Facebook page, or tweet at SciForThePeople anytime. Last but not least, we wanted to let you know our very own Desiree Schell will be moderating a panel at Convergence 2014 in Minnesota this year. Convergence is a science fiction and fantasy convention that includes a great science track filled with awesome science bloggers and scientists, some whom you've heard here on our show before. Convergence this year runs from July 3rd through July 6th, and you can find all the details about this con at www.convergence-con.org. And, as always, thanks for listening to Science for the People.
Science for the People is recorded in Edmonton, Alberta. The show is produced by Rochelle Saunders. Ryan Bromsgrove is our promotions manager. Our social media manager is Chelsea Butler. K.O. Myers updates our website. Helen Quivalon is our publishing liaison. Ed Haynes is our guest coordinator. We get research help from Josh Witten. The show is edited by K.O. Myers and Ryan Bromsgrove. Our theme song was written and recorded by Fractal Pattern, and its title is Binary Consequence. The show is hosted by Rochelle Saunders, Marie Claire Shanahan, and me, Desiree Schell.